Hi, and welcome to this lecture in which we're going to talk about inference for numerical data. I want to do a quick recap in terms of what we've done this far and where everything fits in, just as a reminder. And then we're going to look at the inference for numerical data using R specifically. And remember, this is the follow-up lecture from the earlier one in which we looked at inference for categorical data. Now there's a clear link between what you've done in engineering statistics, BES 220, and this module, industrial analysis, BAN 313. Now, in engineering statistics, we looked at analyzing data. We looked at inference for both numerical and categorical data, and you were exposed to the concept of and introduced to regression if we want to do some predictive modeling. And we always gave you everything that you needed to apply in the formulas. You got your formulas, maybe a formula sheet, and you were given the data and you just had to plug things together. In practice, however, it rarely, if ever, works like this, where you're given the formula and given the associated data that you actually need. If it was that simple, somebody else would have solved it and would not have employed you or asked you to actually do it. So what do we do in BAN 313? Again, we analyze data and we do inference for numerical and categorical data. And if we get to it, we'll do some regression. The difference is we don't give you everything that you need to apply in the formulas. We don't give you the mean and the standard deviation or the different values or the alpha values in some cases. Instead, we give you actual data. And you need to first extract everything from the data that you need. And there may be more data than what you actually need. So you need to be able to filter or wrangle or just muddle through it until you find what you actually need. And sometimes knowing what you need comes with experience, and that's part of the learning process. So remember, how do we solve problems? There's a separate lecture where we talk about our modeling philosophy. Suffice to say that problems exist in the real world, and then we try to imitate those problems or represent them in some form, some abstract form, which we call a model. And then we solve the model and we interpret or infer the results or the solution that actually comes from those models. And then based on those inference or the interpretations, we make a decision which we then go and implement in the problem. Now, up till now, mainly in your second year and maybe still in some other modules, the focus was always on solving the problem. You were given a model, you were given the necessary data, and you had to solve it. You were given a differential equation and say, solve it. Now it becomes a little bit more tricky because our focus, and this is by choice, is to focus on the more vague, more challenging link in terms of moving from the problem to the model. So we give you the problem, we give you the data, and you need to learn which models are actually appropriate in which conditions to actually answer the questions at hand. And it's not always that simple. And very often there are multiple ways of doing it. And you need to become more comfortable and more convinced of your own competence in this case to pick the right model, check that it's a valid model, and then solve it. We don't focus too much on the solving. We expect you to be able to solve them by now, or use software to actually solve them. And then it's also important, the second focus area is to actually infer or interpret the results that you actually get from whatever the model is that you actually chose to employ. Now, if you make the wrong inference or you make the wrong decision, it's game over. It is unfortunately wrong. So the specific focus where we want you to invest your effort and focus your learning on is bridging the gap, picking the right models. So this whole process of modeling and then solving it should be fairly straightforward by now using all of the cool tools that are available out there. And then the second focus area is on inference or interpretation of your results and applying it so that you can make a useful practical decision. So if we conclude in terms of how we solve this, I want to encourage you to not be intimidated by the subject matter. You likely have to refresh your statistical literacy, and the open access and the open source book that we use in engineering statistics is still available, and you are reminded nearly weekly about going back and just brushing up on your statistics. But we are answering the same questions that we did in engineering statistics. The only difference is that we now apply statistical formulas on actual data. In engineering statistics, we told you which method to apply and gave you the parameters necessary for that method. But here in industrial analysis, we may tell you which method to apply, or we will just ask you to justify your answer. Instead of giving you the parameters for the formulas, you have to determine them using the given data. And first, decide which are the appropriate formulas to actually apply to solve the problem or get an answer to the question at hand. Right, let's jump into inference for numerical data. Now, just a pointer, the supporting material is again the book by Dietz and his colleagues from 2014, Introductory Statistics with Randomization and Simulation, and specifically chapter 4, and we go up to and including sections 4.3. So I highly recommend that you go through the material again, read through it. There are a couple of good examples in there, and maybe the explanation is even better than mine. All right, so the first thing when we talk about inference for numerical data, we may just be estimating a single mean. So if you have a large sample, and when we talk about large samples in statistics, we typically talk about more than 30 observations. Then we can calculate the confidence interval, and you've seen these a couple of times now, as the point estimate plus or minus some critical z value, which we call z star, times the standard error. And the standard error is the standard deviation by the square root of the number of samples. Now, we don't have the population standard deviation. What we do have is a sample standard deviation, and for that we change the sigma to an S. Means the same thing, the one only points towards the population, which is what we're actually after, but we don't have it. So we want to make a decision based on the sample that we actually do have. And remember, this Z star, this critical value, depends on how certain do you want to be. The more certain you are, typically the narrower the confidence interval actually get. All right, now, if you only have small samples, meaning n is smaller than 30, and we want to estimate a single mean, then we're going to use a t-distribution with n minus 1 degrees of freedom. So df will denote degrees of freedom, and if you have 10 samples, then you will use 9 degrees of freedom. So the t-distribution looks a lot like the normal distribution, but it has fatter tails. So in the book, in figure 4.5, you actually get a nice illustration showing the t-distribution for different degrees of freedom. And you will see that as you move towards roughly about n equals 30, the t-distribution and the normal distribution are pretty much the same thing. Now, if you have small samples, it's important that we kind of understand and appreciate that we can't be all that certain. And that is why the tails in the t-distribution are typically fatter. There's a higher likelihood that you will actually have values in these two tails. Now, if you want to do inference using the t-distribution, there are two conditions that you actually need to check for. And you're not going to be asked for these conditions. You simply need to apply them and say, oops, sorry, I can't do inference, I need to walk away, or just first test these conditions before you actually move on. And the first one, like we've done in the past, is independence. The data points or the observations in your sample need to be independent. And then the observations should come from a near normal distribution. Now, granted, if you draw a histogram of your observations with very few samples, you don't get a pretty picture that looks like a normal distribution. But you have to at least look for clear outliers. Maybe somebody made a mistake in capturing the data, then there might be reason to remove an outlier, as you'll see in a later demonstration. or at least you need to get some idea of the skewness. Now, this condition may be relaxed if you have a mildly skewed distribution, but you can only do that if you then have samples, let's say between 30 and 60. And for skewed distributions, you need more than 60 samples. Then you can still go ahead and perform the, or use the t-distribution. Right. And then for small samples, if we want to calculate the population mean, we estimate it. That's what that tilde simulation squiggle means. We estimate the population mean with the sample mean plus or minus not a critical z value, but a critical t value. So they're very similar. We call it t star, and we just give it a subscript here at the bottom that says df for a specific degrees of freedom multiplied by the standard error. Right, and we calculate the standard error in exactly the same way. There's a special case in inference for numerical data, and that's when we deal with paired data. Now, two sets of observations are paired if each observation in one set has a special correspondence or a connection with exactly one observation in the other data set. So in the book of deeds, your supporting text, they have a nice example where they actually evaluate the price difference of 73 textbooks as sold by UCLA, which is the University of California in Los Angeles, and Amazon. So for every one of those 73 books, they have a price at UCLA bookstore and they have a price at Amazon. So there's a special connection. Every book has an observation in each of the two data sets. And then to analyze paired data, we simply analyze the difference. Right. So then we can actually have a null hypothesis where we say that the difference in the two means is 0. And the alternative hypothesis would be that the difference between the two data sets, the mean of that difference, is not 0. And then we calculate the standard error of the difference in means as the standard deviation divided by the number of observations of differences that we have. And we calculate the t-value using the observed sample mean of the differences minus the sample mean that we have in our null hypothesis, which is 0, and we divide that by the standard error of the difference in sample means. All right, so that's just a special case when we do inference with numerical data. The third case that we're going to look at is difference of two means. If we have two data sets, but they're not paired, we want to say something about the difference in two population means, mu1 minus mu2. So that's a difference in the two populations under the condition that the data is not paired. And as with a single sample, we identify conditions to ensure that we can actually use the t-distribution with a point estimate. So now we want to say something about the populations difference between two means, but all we have is the sample or the difference of two sample means. Right, and these conditions are each sample in itself must meet the conditions for using the t-distribution, which was independence of observations within the sample, and they should roughly be from a normal distribution or somewhat normal-like distribution. So those are the two conditions for each sample, and then the two samples themselves must also be independent if you want to work with the difference of two means. So we can calculate the confidence interval for our estimate of the difference in population means, as this population difference is best estimated as the difference in the two sample means plus or minus a critical t-star factor for a given degree of freedom multiplied by the standard error of the difference in sample means. And here the standard error for the difference in sample means is calculated as the square root of the sample 1 variance divided by the number of observations in sample 1 plus the fraction of the second sample's variance divided by the number of observations in the second sample. And for the degrees of freedom, we use the smaller of n1 minus 1 or n2 minus 1, where n1 represents the number of observations in the first data set and n2 the number of observations in the second data set. Right, and here when we do a hypothesis test, our null hypothesis is typically that the difference in population means is 0. That's the standard, not so interesting case. And the alternative hypothesis is that this difference, mu1 minus mu2, is actually not 0. All right. We've showed how we calculate the standard error, and now you can calculate this t-value as the observed sample difference minus our null hypothesis case, which in this case is 0, divided by the standard error. It's time to get our hands dirty and demonstrate how we actually perform these calculations in R. And for this class example, we made two data sets available, i.e. salary sample and ME salary sample. And these are two data sets, one for industrial engineers and one for mechanical engineers, that were sampled from random individuals from the Engineering Council of South Africa, for example. And we've got 40 observations in each of these data sets, where we have a tax reference number for each individual in that discipline, as well as the annual salary. And we're going to demonstrate estimating the confidence intervals for one of the samples, and then also look at the difference between the means of these two distributions to see whether the two disciplines actually earn significantly different incomes. So let's jump right into R. Right, I'm going to create a new script file for myself. Cleaning my workspace and loading the library that I will need. So the first thing I'm going to do is demonstrate a single mean estimate, and for that we're going to read in our income. Which is in a data folder relative to where my workspace right now, and I am interested in the IE salary sample. Now, I've looked at the file and I know that it has two columns. The first one is the income reference number and the second is the actual income. So I am just stating my column types. The first one is a character and the second one is a numeric. If you don't know this, you just need to open up your CSV file in a text editor of some sort and just first have a look at the file. Right, so there's the SARS, South African Revenue Services reference number and the annual salary. So we can do a couple of things to investigate the data. We can either call the summary function, we can draw a histogram, or we can draw a box plot. And I can see that the data seems to be fairly symmetric. So I'm going to proceed knowing that these were randomly sampled industrial engineers from the Engineering Council of South Africa, maybe. Assuming that people don't pay one another's salary, the individuals that were sampled. So I'm going to continue and calculate the sample mean. I'm going to calculate the sample standard deviation. And I'm just going to, for ease, calculate the sample size. Right, so I have 40 observations. So I now can carry on to calculate the standard error for the industrial engineers, and that is simply the sample standard deviation divided by the square root of the number of observations. To calculate a t star value, let's make this specifically for industrial engineers. I'm interested to find the actual t value. I know what the probabilities are. Let's say we want to work with a confidence interval of 90%, so 5% at the bottom, 5% at the top. I'm going to use the quantile function for t, similar to the quantile function for the normal or the exponential distribution. The probability that I'm interested is 5% here at the bottom. My degrees of freedom is the number of observations minus 1. And since I'm interested in the lower tail, I will get a t star value. And I see that it is minus 1.68, so it's quite similar to what we see in the standard normal distribution. But since I want to calculate the confidence interval, I want to just use the absolute value. With the standard error and this critical t star value, I can proceed to calculate my lower confidence level, which is my sample mean minus this t star value times the standard error. And similarly, I can calculate the upper level. And then I can just report the two values. All right. And there we've calculated or estimated the confidence interval for a single mean. Now, there's a short version where we can actually do the t-test, and there is a function called the t-test. And I urge you to go and read the help function in R for this function. We're going to provide it a single sample, which will be i.e. income, provided the income values. And I'm interested in a confidence level of 0.9. And here you actually see at the bottom that we get very similar values, in this case exactly the same values for the confidence interval. And this is a one sample t-test because we only gave it the one value. And we can actually get the mean of x as well. All right, so if you're interested in the confidence intervals of a single mean, this is an easy way to actually do it. The first way is exactly the same. That I close that now without saving. So you've got two ways of calculating your confidence interval. Sometimes the values can differ slightly, as you'll see just now. So in the second demonstration, what I want to do is talk about the difference between two means. And for that, we also need to read in the mechanical engineering income. And again, the first column or variable is the SARS reference number and then the income. And I can also call the summary. Or I can call the histogram. Or a box plot. And here I actually see that for the mechanical engineering data, there seems to be a slight skewness. There's one outlier. But if I look at the mean and the median, they are not too far off. And since I have 40 observations for the mechanical engineering incomes, I can deal and still use the t-test with a moderately skewed distribution. So let me just calculate the key parameters that I will need here. First, the mean. The standard deviation. And the number of observations. Right, if I now calculate the standard error of the difference between these two means, I need to calculate it as the square root. And here I have two terms. The first one is the variance, which is the standard deviation squared, divided by the number of industrial engineering observations, plus the variance of the mechanical engineering, income observations, and I can calculate the standard error. Maybe at this point it is worth noting that what I'm kind of moving towards is to have an H0 value that says let's make it mu1 minus mu2 is 0. And my alternative hypothesis is not 0. Or stated otherwise, oops, that should be mu2. Mu1 minus mu2 is not equal to 0. So there's my kind of null and alternative hypothesis. I've got my standard error. And now I actually need to calculate a t-score. And the t-score is the sample observation minus what we would expect under the null hypothesis divided by the standard error. Now in this particular case, my sample observation would be the mean of industrial engineering incomes minus the mean of mechanical engineering incomes. That's what I've observed, and what I would expect in my null hypothesis is 0, and I now divide by the standard error. And I can get a t-score. Right. Now I want to calculate what is the probability that I would have observed what I've observed in terms of the difference in the means if in fact the two distributions are the same and their means are actually 0. And for that I need to calculate a p-value. And I use the distribution function for the t distribution, pt, similar to what I've done in the past for a p-norm or p-exponential distribution. And now I know what my quantile value is because I have calculated my t-score. My degrees of freedom is the lesser of NIE or NME minus, minus 1. And in this particular case, I am going to only calculate the lower tail. But this p-value will only give me one side towards the bottom end of the t distribution. And I'm actually interested in both sides because this is a two-sided hypothesis test. So I'm just going to multiply this probability by 2. And I calculate a probability of 14%. So there is a 14% chance that I would have observed the difference in the two means that I've observed in my samples, given that the differences are actually 0. So there is a fairly sized chance. In the absence of an alpha value, we used, let's say, alpha value of 5% or of 10% even in this case. And I see that my p-value is not smaller than the threshold value, and therefore I cannot reject the null hypothesis. So I cannot conclude. I cannot conclude that there is a significant difference between the two means. And again, there is also a shorter form that we can do this, again using the t-test function, but now we have two samples. First x, which is the IE income value. We have a y, which is the ME income value. And the alternative, and again, you can go and have a look at the t-test help function value here. We're interested in a two-sided, and the data is not paired. And if we run this, it actually uses the Welsh two-sample t-test. And again, we get a p-value which is similar to the p-value that we've calculated. The reason why there's a slight difference here is because they use a Welsh two-sample t-test, which I believe is slightly different. I can get the two means from this test, but what I'm specifically interested in is the p-value, which again is greater than our alpha threshold, so we still cannot reject the null hypothesis. We're not accepting it, but there's not significant evidence to suggest that the incomes of industrial engineering and mechanical engineering graduates are actually different. All right. So have a look at the t-test help function. I think you might find some other insights that you can use to your advantage. Both approaches, using the long way around, I think gives you a good idea of how this black box called the t-test function actually works. So the long way around, the short way around, either one works. We're interested in you making a correct decision in terms of the inference of numerical data.